Hello again, ladies and gentlemen. Mr. Rowney here. We're going to talk about the chatliers principle, which has to do with equilibrium, and we want to be able to predict what kind of change will occur when you stress an equilibrium. So let's take a look at an equilibrium that'll come up a lot. We got N2 gas reacting with 3H2 gas, giving us 2NH3 gas and energy. So this energy is on the product side, which tells us it's exothermic. All right. So this is going to be at equilibrium until we mess with it. And there's different ways we can mess with it. One is by changing the concentration of things, right? So let's see what happens when we change the concentration. All right. So erase all that. So let's say I were to increase the amount of N2. Well, the way I think about it is equilibrium is like a balance, right? We have a certain balance here, and everything's nice and level, balanced. If we're adding more N2, well, that's going to mess up our balance. So we got to somehow get our balance back. So if we keep adding stuff onto the left side, if we increase N2, well, we're going to have to shift our equilibrium to the right so that we can have more N2 and get more energy out of it. So basically, if we add stuff, then we shift away from that side. So we added stuff on the left side, so we had to shift to the right away from that side in order to stay balanced. So let's see what happens if I were to change the H2 concentration. Well, if I add more H2, the same thing's going to happen. Right? I'm going to have to shift to the right, which means I'm going to increase my NH3 and my energy being given off in order to maintain that balance. Now I have a question for you that I didn't talk about on the last example. If I'm shifting to the right, what's going to happen to the amount of N2? Well, if I'm making more product, then I'm using up reacting. So we're decreasing the amount of N2. We added more H2, well, we got to get rid of that by making more NH3, and we can only do that by using N2. All right? Well, what would happen if I were to remove stuff? Right? So let's say I were to remove N2, I were to subtract some. Well, again, think of it like a balance. If I'm removing stuff from the left side, I'm going to have to replace it. Right? This side became too light. I need to make more stuff on that side in order to stay balanced. So if we remove, we got to replace. So add goes away. You remove it, you got to replace it. So now if I removed N2, I'd have to replace it by shifting to the left, which means I'm going to increase my H2 because I'm shifting towards it, and I'm decreasing the amount of NH3 and decreasing the amount of energy. All right, so let's see what happens when I mess with H2 in the same way. Let's say I were to remove H2. All right, again, if I remove stuff, I got to replace it. So I'm shifting towards that removal to replace the stuff I got rid of, which means I'm going to use more, or I'm sorry, not use, but make more N2. How can I make more N2? Well, you got to use up some NH3. So if we shift to the left, we use up the stuff on the right side and it goes down, right? I'm also going to lose energy. All right. So now let's see what happens when we mess with NH3, our product. All right, well, I can add more NH3. And now let's think about this. If it's a balance and I add stuff onto one side of it, I'm going to have to shift away from it in order to stay balanced. So I'm going to have to shift to the left. All right, which means I'm going to make more H2 and more N2. They're going to increase because I'm shifting towards them. And I'm going to have to use up some energy, so I'm going to run out of that. All right. All right, well, what if I did the opposite? What if I removed NH3? If I removed NH3, well, then I got to replace it. So I shift to the right, which means I'm using up N2, I'm using up H2, and I'm going to replace the NH3 that I removed. All right, the energy is also going to increase because I'm shifting towards that. So add, we got to shift away from what we added. If we remove stuff, we got to replace it, so we shift towards it. Now, if we shift towards something, then it increases, right? If I'm shifting towards NH3, I'm increasing than H3. If I'm shifting towards the energy, I'm increasing energy. If we shift away, guess what it does? It goes down, right? Because we're using it up. I'm shifting away from H2, which means I'm using more H2, which means I'm running out of H2. All right, so that's, you can mess with concentrations, and that's what's happened. Temperature isn't all that different. All right, you got to just treat temperature like it was one of the chemicals in there, right? Like just same thing. Let's say we were to increase the temperature. Well, how do we do that? That's like saying we're adding energy, right? So we just treat it like the same thing. If I'm adding energy by increasing the temperature, well, I'm going to have to shift away from it, which means I'm going to make more H2, I'm going to make more N2, and I'm going to use up NH3. So it's the same thing. If you add, you shift away. Right? All right, well, what happens if I were to decrease the temperature, if I were to remove heat? So decrease temperature, you're basically doing the same thing as removing energy. So same rule as if you were removing anything. If I'm decreasing energy, I'm going to have to shift to replace that energy, which means NH3 is going to increase. H2 is going to decrease because I got to use it up, and same thing with N2. Right? Not so bad, kind of straightforward. Now pressure's different. Pressure only affects gas. Right? Pressure doesn't affect liquids or solids. And pressure, if we were to increase the pressure, it will not, it's going to favor the side with less gas. So let's take a look. I have N2 gas, so that gives me 1 gas. And I have 3 H2 gas, so I have 1 and 3. That gives me 4 gases on the reactant side. Now I take a look. I have 2 gases on the product side. So it's 4 versus 2. I got more gas on my reactant side than my products. So if I were to increase the pressure, let's say pressure goes up, which way am I going to shift? I'm going to shift towards the side with less gas. I'm going to have to shift to the right. Now let's think about this. It kind of makes sense, right? If you got a bunch of gas and you're increasing the pressure and trying to compress it, it's going to be easier to do that if you have less gas. So more pressure, the more you got to compress it, it's going to shift it towards the side with less gas. In this case, to the right, because there's only 2 on that side. Now the opposite is true. If I were to decrease the pressure, well, if I am decreasing the pressure, I'm pretty much making more room for gas, so I can have more gases. So it would have to shift to the left, the side with more gas. So if I decrease pressure, it favors side with less gas. I'm sorry, more gas. Derp. Actions. So less pressure, more gas. More pressure, less gas. Right? So that's pressure. Now, catalyst, and I put question marks there because it's like, what would a catalyst do? Well, what do catalysts do? They speed things up. They speed up reactions. All right. So you got to remember, in equilibrium, there's a forward reaction and a reverse reaction. And a catalyst is going to speed both of them up. It's like saying, hey, I'm going to turn this treadmill up. I'm going to make it go a lot faster, but I'm also going to make the person on the treadmill run faster. So overall, there is no change. So catalysts, equilibrium, no change. Because you're speeding up both the forward and the reverse reaction. They're both going faster, right? Or it's like somebody trying to walk up a down escalator and then somebody cranks up the down escalator and then they start running up as fast as they can, but they're still staying in the same spot. Both reactions are increasing in rate. So yeah, those are the ways equilibrium are affected by changes, and I'll try applying them to new situations, and see you in class.